Hello and welcome. If you'd like to know about maze generation in GameMaker Studio 2, you've come to the right place. We're going to do just a quick example, little overview. So let's just hop right into it, shall we? So over here, I've started little paint. So this is how the maze would start, right? It's a fully filled in grid, all the walls are there, and you want to traverse through the maze, right? So start at starting point, and it's going to travel as far as it can until it hits a dead end. So it's going to look at its options, and it's going to go, oh, I want to go this way, right? And then he'll be there. Wow, paint is awful. So he's going to go there. It's going to remove this wall, and then from here he'll go here, and then he might travel over here until he backs himself into a corner, which would happen down here. Now, when he's down here, he's going to find out there's no more spaces to go. At this point, the algorithm is going to just follow the path back, and he's going to find, oh, this one has options, and it will perform the algorithm from there. And as it goes through the maze, it will knock out the walls as it goes through. That not right. The path that I took, right? It's going to knock out these walls, and eventually you're going to be left with a good old-fashioned maze. So enough of that. Each cell, right, then in the maze, we're going to need to know if it's been visited, because once it's visited once, you can't go back to it. So you can't like knock out any more wall. Well, you can knock out walls technically, but and each cell only needs to keep track of its right wall and the wall underneath it, because you'll see in this first cell, make a little rectangle around it. So that is a solid rectangle. Right, no fill. Sure, there we go. So you see it's got the right wall and the wall below it, and then the cell below it also has that, right? And each cell below that, and it follows for all the cells until you get down to here where it's got this right wall and this wall below it, which should never get knocked out. Likewise with all of these. And you'll notice, yes, there's no left side of the maze or top side of the maze, but that's easy to draw in yourself. Very easy. So that's pretty simple. We're going to utilize a few important features. If you check the manual or the code base, we are going to be utilizing some stacks, which if you need to know more about stacks, you can easily just baffling. This is very interesting. Have not used this in a hot minute. You have DS stacks. We're going to utilize stacks, which are pretty, fairly simple data structures. If you want to read more about that, I'll post a link to where you can find more information about that. We're also going to utilize the list data structure, and that is simply so that we can choose which directions we're going to move in. So we're just going to get started. We're going to make all of this in a single script, a couple different functions. So I'm just going to call this mazes for now. We're not going to keep that name. So the first thing we're going to do is we're going to make a constructor if we want to make like a maze object, right, that contains all of its information. And this maze object, we're going to want it to have the, we're going to call it the style, the width, and the height. Now, the style, this is basically just a parameter that's used to determine how the maze weights its direction. So when it chooses which to go right or down, left or up, it takes all those directions and it runs it through whatever style we're using. So for this example, style of 0 is going to be completely random. It's just going to choose a random direction. That's what we're going to stick to. You can modify the weights, and that you can do some more interesting stuff, like you can make spiral patterns, semi-random spiral patterns are possible too. So in this, we're going to just have the grid variable. This is just the entire grid of the maze. We don't have to initialize a 2D array because GameMaker will allocate and just resize it as we go along. And then we have its style, the width, the height, which those are all passed in. And then this, you could make it a parameter, but for this example, I'm just going to put it in here. We're going to have a start point. We are, for the sake of this, we're just going to start at the top left corner, and we are going to end at the bottom right corner, which would be width -1, height -1, since the indexing will go from 0 to 1 minus the width, which from 0 to that is a width of whatever you pass in. So then we just want to initialize the grid. So we use a double for loop, less than the width, I less than the width, increment I, and then we want to handle moving vertically. And then here you're going to realize that we have the grid at ij, and that's going to need to be the grid space. So we're going to need some variables, and we're going to realize, oh, well, we need another struct that's going to exist within this struct. So we're going to make that really simply. So we are going to ignore this for now, and we're going to come down here. Let me scroll over here. And we're going to create another struct. And I just caught this. It should say constructor. That's my bad. That means if you create a new maze, it will have all these variables. It's like an object, but without all of the predefined variables that come with it, such as, you know, all the image stuff, the location, because we don't need a location for this. It's just a clump of data. So we are going to make, this will be a maze grid space. Doesn't need any parameters because they all start the same. It's just going to have visited is false, and then I'm going to say right equals true. This means that the right wall exists and the wall below it, so down, also equals true. This means they haven't been knocked out yet. This will be the initial state that will give us our initial prescribed grid. And from there, we will starting point and start knocking out walls. And we're going to use an algorithm that is very common for maze generation. It's probably one of the simplest. It's just a depth first backtracking. You can make it recursive. We're just going to use a while loop just because it's quite simple. It's all you need, and we're not doing anything super complicated because games don't typically require very advanced maze generation unless you really want to get fancy. You could custom make some mazes, So now we're just going to get right into it. We're going to do, this will be the bulk of the algorithm here. So this function that we're going to make is just, I'm going to call it maze generate, and it takes in a maze struct as its parameter. So it's going to take a maze that was already generated, and it's going to modify it so that the grid becomes a maze. So quite simply, we're going to start with the stack, because we want to keep track of where we're currently forging our path through. So we're going to create a stack, and we're going to call it branches, because these are all the points that we can branch off from. And then we are going to localize the maze structs grid into a local variable called G, because it's easier than typing out maze struct.grid every time. You can just do G and then access you can index it that way. And then we're going to create another local variable called CP, and this is going to stand for current point. This is the current point that we're working with, so it's going to be the start point, obviously. So it's going to be the maze struct dot start point, and it's going to be the x value, and then you want the y value, which is index 1 of start point, and that will give you the current point. Now, since we're essentially at this current point, and it's going to be added to the top of the stack to start us off, when we loop through the stack, we're going to set it to active, because we're at this point now, it's active. So G at CP 0 and CP 1 dot active going to equal true. And I called that visited. That's on me. In my other example, the other one I wrote, I called it active. We're going to stick to visited though, because I feel like that is a much better description. So visited will be true. And now here, let me enlarge in this so it's easier to see. So now from there, also I'll make this a little, can I make this bigger? Well, anyway, and then we're gonna use ds stack push to push this point onto the stack, because that's where we're gonna start. And that is the prep work. This is all just the prep. Then we can enter the bulk. So we're going to loop. We're going to loop until the ds stack is empty, because once it's empty, it means there are no possible branches, meaning every point in our grid has been visited and we should have a maze. Plain and simple. So to do that, we're going to say while the ds stack is not empty. So while it's not empty, we want to read the top of the stack. So we're going to localize it again, right? So we're going to say our CP equals ds stack top. This will retrieve the top of the stack without popping it off, because we don't necessarily want to pop it off, because if there's more than one direction we can take, we want to be able to come back at some point and branch out, potentially. So after we get the current point, what we need to know all of the possible directions we can move. So we're going to gather the potential directions to move. And this, quite simply, is the easiest way I found to do it is to store all of them in a list, because then you can modify the list how you see fit with other styles. Randomness, basically for random, we're going to put all the possible directions, and by directions I mean the points that we can travel to, into this list, and we're going to shuffle the list, and we're just going to pick the first one. So we're not worried about any sort of weights, like is going right weighted heavier than going down or up, stuff like that. And to do this, we're going to quite literally just use 4 if statements, because there's 4 possible directions, and we're just going to keep it as simple as possible. So we're going to check to the left of the current space. So we want to make sure that we are not on the edge. So the x value of the current point is greater than 0, and we want to make sure that, here, let me type it real quick. It is a handful here. So what we're checking here is we're checking the grid space. I believe that has everything. Yeah, the grid space at the point to our left. And we're going to make sure that visited is false. So we do that by putting the exclamation point here. And if all of this is true, that means that we are able to add this point to the list of potential directions. So we're going to add CP0 minus 1, comma, CP1. Yeah. And that adds that. And then simply we're going to do this. Here, let me center this a little bit more. And then we're going to do the same thing to the right, which is very similar. So instead, you're going to make sure that our x value is less than the maze structs with -1, because it goes to -1, so you want to make sure you're less than that index-wise. And then this minus becomes a plus to check the right. And then when we add it, obviously this is a plus. Now, we're going to check above us, which is, we're going to make sure that the y value is greater than 0. And then we're going to make sure that the point above us has not been visited. Yep, that looks right. So I'm going to tab this out just to make it all the same. Yes, let's add to P direction, add CP0, comma, CP1 minus 1. And then close that off. And then there's just one left, obviously checking below us. And yes, I know this is extremely repetitive, but I found that it's just the simplest way, because you're only going to have 4 directions. There's not, if anybody knows a simpler way, I would love to see it. It would be amazing. Especially if it's less code, it's simpler. And you could put this into its own function. However, we only need to do it once right here. If we were doing this a lot, checking lots of neighbors, then it would make sense to put it in a function, just so you don't have to type it or copy and paste it a lot. But so after we've gathered all of the potential directions, it is time to then we perform our weighted assessment. So we want to check if Peter is empty, right? Because if the stack is empty, that means there are no potential paths to take. And we're going to pop the stack, right? So the point that we're at should not be on the stack that we're working with. We don't need it anymore. We're going to pop the top off of the branches stack. But if it's not empty, that means there's somewhere to move. So being random, and I'm going to make this, so our maze has a style. So style 0 is going to be random. So what we can do is we can use a switch statement. First, we're going to set up the new point variable. It's going to be 0 for now. This is just to localize it outside of the switch statement for easy accessibility. So we're going to use a switch for the maze structs style. And now I'm going to say case 0. And so this will be the completely random. This is arguably about this is about as short as it gets for weighting the edges, and as simple as it gets. So basically, we're just going to take the list, and this is why I used a list, because ds_list has a shuffle function. Otherwise, if you just used a regular array, you would have to shuffle it yourself, which you'd have to write yourself, which isn't difficult. It's just this already exists native to the language, so why not utilize it? And then we're going to set the new point as whatever is at the top of this list. Because it's not empty, 0 will always return a value. Even if there was only one value and it can't shuffle one value, this will still give us the first one. And so outside of the switch, now normally you'd want to add a default. I might default this if you remove the 0 and default it, so that if someone tries to enter a style that you haven't set up, it doesn't just break your code. So you could always set up a default case right below it by just, yeah. But we're not going to worry about that. We're not going to misuse this. So outside the switch statement, so now we have the next point that we want to go to. So we want to set that point to active, because that'll be the new point. So we'll say g of np0 and np1 dot visited. Sorry, I keep saying active. We're going to say visited because now we have, we're going to say we've officially visited that point, and we are going to push this point on top of the stack that we've been working with. This way, when we finish our while loop at the beginning here, it will pull right here. It'll pull, the current point will now be the new point that we've added to the top of the stack, which is exactly what we want. Now we want to determine which walls to break, which is another case of just 4 if statements that you don't have to do anywhere else. So we're just going to do them right here. So you want to check if we want to break the wall to the right, the wall below us, or we're going to have to break the right wall of the neighbor to the left, or the down wall of the neighbor above, which sounds a little more complicated than it is. Graphically, it is this is a mess. Let's say here, let me use purple. Let's use purple on this point. So if we're here, right, and we move below us, right, not there I wanted, and we move below us, we're going to compare the x value, right, of these, and we're going to see it's the same, right? So we're not going to break any right walls, but we're going to see that the y value, or this tile is below the one we were just in, so we're going to break the wall of the one we were just in. That's just how it is. So if we came from this way, we want to break the right wall over here. So this is why we set up to only have right walls and down walls. It's simpler. It might seem a little complicated in the short term, but it's definitely shorter, less work. So I'm going to check if the new point is to the right of the old point, then we're going to break the wall, the right wall of the current point, which is CP. So that wall becomes false. And then we're going to check if the new point is to the left of the old point, we're going to break out the wall of the new point. Oops. The right, and that is going to equal false then. And then we need to handle the vertical cases. So if NP1 is greater than CP1, it means the new point is below the current point. Break out the down wall of the current point. It's a mouthful to say, but once you get it and type it all out, it isn't too bad. Yeah. And I'm just going to copy and paste this to maybe save a little time. It might save no time at all in reality. P. So those will be the cases for breaking the walls. Now, after, let's see here, what is this? Yeah, so after we're going to pop it, Peter, and everything. Since we're done with this list for now, we are going to destroy the list because we don't want it taking up memory. That is just a good practice because if you have a large maze, you're going to have a lot of lists. So you want to keep up with those. And then after this, that should be the end of the while loop. So once the while loop is finished, we want to destroy that stack. Even though it's empty, we're going to destroy it just so when you create a new stack, it'll just start at the beginning. It won't have to use the next integer for the stack value ID. So we're going to destroy the branches stack. And that is really all there is to it, to generating the maze. That is the bulk of it. And to demonstrate this, we are going to just create a little function that will draw it. Just to display that it's working, because obviously after all this, you want to check and make sure it is working. So I'm going to just copy and paste it over. If you want to pause the video and pause the video after let me make sure this doesn't depend on actives, right? Okay, this should work totally fine. Maze struct, cell size, offset. Basically, if you don't want it drawn in the top left, you can offset the X and the Y. This is the maze struct. Cell size, just the size of each little box in the grid. It's going to go through the grid. It's going to highlight the start and the end point, which you can always change. So this is dynamic. This should work. So I'm going to go ahead and modify the room a little bit just to make it how I like it. I'm going to make it 1600. That's not 1600 by 900. And I'm going to create an object to test this. Call it O maze test. And it's going to be super simple. Create event is going to, we're going to create the maze test. It's going to equal maze style 0 width we're gonna do 200 by, we're gonna do 100. We'll do 200 by, we'll do we'll do 100 by 100, and then we'll generate it. Oops, maze generate, and we put maze test into it. And then we're just going to quickly draw this to the screen. I'm going to say draw maze. I'm going to draw our maze test. Cell size, we're going to use 8. Offset is going to be 400. And then, let's see, its height 100, so 50. So this will just center it within the room. Obviously, you can do this however you like. Hopefully, I pray that I didn't copy anything wrong, so I don't have to edit this. Hopefully this works. It probably won't. I didn't put the object into the room. So now I guess we'll see if this works. Probably going to error out somewhere because I copied it wrong. Right. Oh, I know what I did. I see this is the problem with anything. You're always gonna have to debug it, and I know what I did wrong because with structs, you need to put new because you're creating a new instanced struct into the world. Good. Good. Visited. Unknown object. So I will cut this out real quick. Let's just figure out what the hell's going on. Okay, after a little bit of deliberation, I have figured out that the problem is here. We need to make a new maze grid space. I don't think we were doing that. I pray it works this time. It works in my other folder. So, right, something's not an array. Is it not? Is it not though? NP should most certainly, okay, be an array. NP Peter 0. When we make this, this is most certainly an array. So I'll figure this out. I am back after much deliberation and debug messages and whatnot. I can confidently say that you might have caught it when you were typing it because you said that's weird. Right here, I'm checking if the stack is empty. Peter is not empty. It's not a stack. It's a list. So that hopefully fix everything. And it does. You get an incredibly well-made maze, completely random start to finish. And this is implementable, you know, in a game if you want to have a big old maze. You have lots of, you could use basically a generated dungeon essentially where you have to get collectibles, fight enemies, whatever you really want. This is what you can do. If you have any questions though, let me know. I will post a link to the project files. If you want to download them, you can check them out, play around with it. All right, well, I hope this has been helpful through our struggles with the code, but thank you for watching.